So this second lecture will be in the same spirit as the first one. I will just continue the overview of TT theory, and the main goal is to provide context and motivation for the more concrete thing we'll be doing starting tomorrow. And so even if starting tomorrow we'll focus on quiver with potentials and we'll mainly focus on this kind of very simple looking stability conditions, parts of what we'll do tomorrow for quivers is actually motivated by some story happening in some geometric context. So in this lecture, I will continue discussing both the quivers examples and geometric type examples. And so this thing was one way to produce stability conditions for a quiver with potentials. And add these two other classes of examples, like current shifts on the Calabi-Yau variety or Fukaya category of a Calabi-Yau symplectic manifold. And you might ask, what about stability conditions there? So I will first start with a symplectic story. And this symplectic story, it will be mostly heuristic, but actually it gives quite a lot of motivation for a lot of things which we'll eventually do. So if you start with Y, a compact Calabi-Yau manifold, and here I start with a Keller context. So I have J, a complex structure. I will have a complex manifold. And I assume it's Keller. It admits Keller forms. And I have this Calabi-Yau condition that the canonical line boundary is trivial. And I pick omega y, which is a holomorphic volume form, so a trivialization of ky. And in this context, if you fix alpha in H2 of X with dual coefficient to Keller class, so class in cohomology which can be represented by a Keller form, then by Yau's theorem proving Calabi conjecture, there is this differential geometric statement telling you can find a Calabi-Yau metric. You can find a Ricci flat Riemannian metric, which is scalar with respect to the complex structure, and with scalar form omega lives in this Keller class alpha. And here I wrote down one way you can characterize a Ricci flat metric. On one side, you have the Keller form omega, and you consider omega to the d, where d here is a complex dimension. So omega to the d is a top degree differential form. And you want this top degree differential form to be essentially equal up to some constant factors to this other top degree form you can cook up, which is a volume form omega wedge omega bar. And now if you have L inside Y, a Lagrangian submanifold, you can look at your holomorphic volume form omega y, and you can restrict it to L. And you will get the top degree differential form on L. And you can write this form as being a function times the volume form on L defined by the metric on L, which is a restriction of the metric on Y. And something which follows from this Ricci flat equation is that this function on L is like a smooth function which is valued in U1, in like complex numbers of modulus 1. And so for any Lagrangian, if you have this Calabi-Yau metric, you can cook up this function FL. And then, so FL is defined using the holomorphic volume form omega y. And you say that L is a special Lagrangian submanifold of phase theta if this function FL is actually a constant function. And if it's a constant of modulus 1, it has to be just e to the I theta for some theta. And if it happens, we say that L is Lagrangian, is special Lagrangian of phase theta. So what is important here is that the notion of Lagrangian submanifold only depend on the symplectic structure, only depend on small omega, whereas the notion of special Lagrangian depends crucially on this holomorphic volume form omega y. It depends crucially on the complex structure. And the general expectation I will review on the other slides is that these special Lagrangians should be some kind of stable objects for appropriate stability conditions on the Fukaya category. So in my general discussion of stability, I have this lattice gamma, and I wanted to have a map from K0 of the category to gamma. And here the natural group gamma to take is a middle degree cohomology of X, so HD of XZ. And indeed, there is a natural map from the K group to gamma, because if you have a Lagrangian submanifold L, you can simply look at the homology class of L. It's a middle dimensional homology class. So I take gamma being this lattice. And then the general expectation, which goes back to at least some paper of Thomas and Yao, and there is some more recent paper of Dominic Joyce explaining some details or criticizing the proposals, is that in the previous context, so if you have the simplicity manifold Y and omega, and if you have actually a complex structure J, so that omega is scalar with respect to J, and so you get this omega Y, then there should exist a corresponding Bridgian stability condition on the Fukaya category. And the expectation is that the central charge, or this stability function Z, should be the map from gamma to C, which is given by the periods of this holomorphic volume form omega Y. So if you have a middle dimensional homology cycle gamma, which you think as being the class of a Lagrangian submanifold, you can simply integrate your holomorphic volume form on it, and you get a complex number. And the kind of vague expectation is that for these hypothetical stability conditions, the stable objects of phase theta should be roughly related to special Lagrangian submanifolds of phase theta. And so in general, this thing is only an expectation or a conjecture. And there are many reasons for that. So the first main reason is that the Fukaya category is a complicated object. And the related difficulty is that a special Lagrangian submanifolds are maybe even more complicated objects that are defined by some this kind of differential geometric story, which are reviewed here. And if you think about the definition of a stability condition, one of the key points is this other Narasimhan property, telling us that if you take any object in your abelian category, it is kind of made of semi-stable. This is filtration whose quotients are semi-stables. And the naive reason to expect something like this conjecture is that if you take any object, something like a Lagrangian submanifold, it might not be special Lagrangian, but you might try to make it special Lagrangian by flowing some appropriate differential geometric flow, some mean curvature type of flow. And if you follow this flow, sometime you might make your Lagrangian special Lagrangian, and then you are done. You are fine, semi-stable. But in general, along this flow, your Lagrangian could develop some singularity. And then you should do some kind of surgery, and then continue the flow until each of the pieces becomes special Lagrangians, and you get your kind of harder Narasimhan type filtration. And so to realize this picture, there will really be an enormous amount of differential geometric or analytic difficulty having to do. How do you do this kind of flow with surgery, which is supposed to, at the end of the day, produce you the required special Lagrangians, making your general object. And there is obviously a related difficulty that actually the definition of the Fukaya category itself is more complicated than just talking about Lagrangians, so there is a lot of issues there. Nevertheless, this picture will be motivational for many of the things we'll do. In particular, here is there's a clear expectation for what Z should be, and there is there's just a very simple formula for Z, just some integral of omega, even if what A is unclear. Yes?
Are there cases in which this has been proved?
So I think the only cases where versions of that have been proved is if Y is like complex dimension 1, so real dimension 2. And the point being that, okay, if you are a real dimension 2, just like, okay, so you might, if you really insist on Calabi-Yau, it's just an elliptic curve, but maybe if you broaden a little bit your context, you might consider like marginal topological surfaces. And then in this case, like a Lagrangian, actually any curves on your surface will be Lagrangian some manifold. And being special Lagrangian will be something like being a straight line for a natural metric, flat metric. And then you can prove that, and the kind of thing you need to prove is something like a general curve. If you deform it, you can make it into maybe a union of straight lines. And doing the analysis for that is not so difficult because curves and lines are not so difficult. So there have been some work in this kind of very, very like lowest possible dimension in which you can realize this kind of picture.
And in the case in which y is the cotangent of some other space, it's easier since the Fukaya category has a different description in the case as some static sheaves and so on. I mean,
Yeah, that's so maybe this thing is actually a good question. In the case where you have some kind of constructible sheaf description of the Fukaya category, does it help to address this question? Actually, I don't know. So probably it could help, actually, yeah, the short answer is I don't know, but probably it could help to define the stability, maybe. But then to relate it to the kind of original, like geometric looking expectation, I will not know how to do that. So I don't think anyone has done that actually currently to maybe use this kind of alternative looking definition of the Fukaya category to address this question. I don't think it has been done. But yeah, yes, good question. Yes, part of the issue of this conjecture that maybe the existing definition of category is maybe a bit too complicated to even think about this conjecture, but maybe there are better definitions. It will be better. So this thing was on the symplectic side, and now what about the DB-Co side, so derived category on the compact Calabi-Yau? So in this case, the natural choice for gamma, and maybe what I wrote should be twisted a little bit, but roughly you can consider the Chern character going from the K group of X to the even comodulo of X with rational coefficient. And you can look at the image of that. And then the kind of very general expectation is that you should be able to produce Bridgian stability conditions in your derived category of current sheaves on X, starting from what I denote by M tilde, which is some kind of universal cover of a stringy Keller moduli space on X. And for general X, it's unclear what it is. So if you happen to know mirror symmetry for X, then this space should be something like a moduli space of a complex structure on the mirror. And the only thing which maybe is kind of expected in full generality is that, so this picture here is supposed to be a very vague picture of one of these space. And in this space, there are particular ways to go to infinity. In particular, there should be so-called large volume point, which are determined by choice of a non-pole line bundle L on X. And so here in this picture, I put some kind of direction, go to infinity in some direction prescribed by a choice of on-pole line bundle L. And the thing which is expected is that so inside the space of Bridgian stability conditions, this picture should sit. And if you go following this direction, the art of your Bridgian stability condition should become closer and closer to the obvious art given by the current sheaves on X. And the notion of stability given by your Bridgian stability condition should become closer and closer to well-known algebraic geometric notion of stability, which is Giesecker stability for current sheaves on X with respect to the on-pole line bundle L. So here, the point of this slide is that in general, we don't really know what this picture looks like, but like near infinity, we know what it is supposed to reduce to. So near infinity, it's supposed to reduce to this classical notion of Giesecker stability or semi-stability. So if you have L on-pole line bundle on X, and if you have E a current sheaf, you can consider its Hilbert polynomial, which is the Euler characteristic of E tensor by L to the n, viewed as a function of n. So this thing is a polynomial in n, the Hilbert polynomial. And so for a fixed E, you can look what is the leading term of this polynomial, and you normalize your polynomial by dividing by the leading term. And then you say that your sheaf is Gieseker stable or Gieseker semi-stable with respect to L. If E satisfies some kind of geometric condition, it is of pure dimension. So for example, if E is some kind of positive rank, it will say something like E is torsion-free. And the important condition is the second one, saying that for every F a strict subobject, then this reduced Hilbert polynomial of the subobject should be less than the Hilbert polynomial of E. Yes?
Okay. Can I ask you a question about the previous slide?
Yes.
In the case in which you have a K3 or an elliptic curve, is it clear what is this M or M tilde?
Yeah, so for an elliptic curve, it's known what this is M tilde. One way to say it is that because we know that the mirror of an elliptic curve, it's another elliptic curve. And so this M will be the kind of the complex moduli of this elliptic curve. So it will really roughly be some upper half plane, or maybe some upper half plane mod SL2Z. And I think already for K3 surface, I think it's not known how to make this global picture. So probably we know, if you set these things properly, we know what M tilde should be. But like constructing this map, I think is not done. It's done partially, like near this point. Maybe there is like, maybe it's known that maybe like this part of the picture can be put into the space of Bridger stability conditions, maybe. But I don't know that the full picture is not. Yeah. So concretely, yeah, what algebra geometry have managed to do in most of the cases is realize this part of the picture, proving that if you are near this large volume point, you can cook up some Bridger stability conditions, which in nice cases like cover some kind of neighborhood of this point.
So just to be clear, it is easy to show that Gieseker stability gives stability condition in the sense of Bridger.
Yeah, so it's part of the issue that Gieseker stability does not give a Bridger stability condition except in dimension 1. And one way to express the issue is that we are really comparing some polynomials. So we are really comparing like a bunch of coefficients. So it's not like one inequality, but it's like successive inequalities. Whereas to phrase it in the Bridger language, you need a single inequality. So in dimension 1, this Gieseker story reduces to this stability for sheaves on curves, which is here. And here there is essentially only one coefficient, which is this degree divided by rank. And so you can turn that into a Bridger stability conditions. But in general, it's not. So actually, there is some general statement like saying like the current sheaves can never be the heart of a Bridger stability condition if X of dimension 2 or more. So here the expectation is that Gieseker stability does not satisfy all the axiom of Bridger stability condition, but it's a kind of asymptotic version. So it lives somewhat infinity. So what I mean by that concretely, what this thing means concretely, is that if you fix some class gamma, then your moduli space of stable objects with respect to the Bridger stability condition, if you move far enough toward infinity, at some point it will agree with the moduli space of Gieseker semi-stable objects. So yeah, so it's part of the issue. So actually, in the geometric context, to produce any non-trivial Bridger stability condition is actually a non-trivial task. And one of the issues is that this Gieseker 1 is not an example. So Gieseker 1 is only some kind of point at infinity, like outside the space. And what you want to do is to really like get a neighborhood of this point at infinity.
Is there a way to compactify stub in a way that it disappears?
Yeah, that's, so indeed it's a natural question, and I don't know. So I think there are various proposals for how to compactify stub, and I think they are not all equivalent. So yeah, you might hope for that. And definitely there are some notion of like maybe like weak stability, which include Gieseker stability. But I don't think there is yet a fully agreed upon theory of compactifying moduli space of stability conditions, which will do what you want. But definitely it's something that people have been thinking about. So it was all for stability. So if you remember, our kind of final goal is to count stable objects. So before counting, we'll like to talk about moduli spaces of stable objects. And so if I come back to a quite general setup where C is a smooth and proper triangulated category, maybe with some DG enhancement, and if sigma is a Bridgian stability condition, that is the data of this A and Z, and that's this latest this choice of gamma, which is maybe implicit. And if I fix gamma, small gamma, and big gamma, I can look at all the possible objects of class gamma inside the abelian category A. And I denote that by this mat frac type M gamma. And if you are lucky, and probably with the correct assumptions I wrote down, you can really show that this M gamma has a natural structure of a stack. There is just a big algebraic stack of objects of class gamma in your abelian category. So they are just all possible objects. And then inside it, you have the one which are semi-stable. So the substack M gamma, I'm denoting M gamma sigma semi-stable for a stack of semi-stable objects. And inside it, you have the stack of stable objects, M gamma sigma stable. And yeah, maybe the kind of, before continuing the general discussion, maybe the example you should have in mind is just if you think about quiver representations. If you think of the abelian category of quiver representations, if you think about what are all possible quiver representations with the dimension vector gamma, then you need to give yourself some vector spaces of dimension gamma I over every vertex I. So they are just copies of C to the gamma I. And so the honest data is the data of the linear map from any arrow alpha from I to J. You need to give yourself a map from C to the gamma I to C to the gamma J. So you need to give you a gamma I times gamma J matrix. So there is a C to the power gamma I, gamma J worth of choices. But then you should really consider isomorphism classes of representations. And the two such representations are isomorphic if they differ by the action of the product of the I of the general linear group GL gamma IC, just acting by linear transformation on the complex, on all of the complex vector spaces. So in the quiver context, this stack of all possible objects is just this stack quotient of this big vector space by the action of this product of general linear group. And but we don't care about all possible objects. We care about the semi-stable or the stable one. And under nice conditions, this stack of semi-stable or stable objects will have some underlying good moduli spaces, which will no longer be horrible out in stacks, but some honest scheme or algebraic varieties. So you will get some M gamma sigma stable, some kind of coarse moduli space of stable objects inside M gamma sigma semi-stable. So what I mean by straight M, they are kind of coarse moduli spaces. Maybe in the classical setup of sheaves, M gamma sigma semi-stable is really the moduli spaces of S equivalence classes of semi-stable objects. You identify semi-stable objects which have the same Jordan-Holder filtration by stable objects. And this thing would be like honest scheme, and under appropriate properness condition on your category, the moduli space of sigma semi-stable will be a proper scheme. Okay, so here's the relation. So the relation between these stacks and these schemes, so you can, they are like natural maps. And what happens over the stables is kind of easy because we recalled previously that a stable object has only a C star worth of automorphism. So the only difference between this stack of stable object and this coarse moduli space of a stable object comes from this C star automorphism. So like for every point downstairs, there is a point mod C star upstairs. What is more tricky is what happens for semi-stables, because semi-stables can have much larger automorphism groups. And so the structure of this map from this stack of semi-stable to this coarse moduli space is much more tricky. And essentially, all of the difficulties we'll be talking about later come from the difficulties hidden in this map. So if I come back to the example of Fourier representations, the matrix M gamma is just a stack quotient. And then the straight M gamma, it's a GIT version of this quotient, so which will no longer produce a stack, but some honest algebraic variety. And the choice of the GIT parameter is related to the choice of stability for the quiver. So in the setup of king stability, every choice of king stability gives you a particular way to do this GIT quotient, and so give you some moduli spaces which depend on the stability parameter. So I have this M gamma depending on sigma. And if you're in the geometric context, if you believe that the moduli spaces you care about in some appropriate limit should be moduli spaces of Gieseker semi-stable sheaves, in algebraic geometry there is a well-developed theory of moduli spaces of Gieseker semi-stable sheaves of smooth projective variety that, again, at the end of the day, you can describe using a geometric invariant theory. So both of these spaces are kind of examples, they're kind of well-known spaces, and what I'm trying to say is that they are kind of concrete examples of maybe the general theory of looking at coarse moduli spaces of semi-stable objects. So for a general category, you have these moduli stacks of all possible objects, maybe moduli stacks of semi-stable, and maybe coarse moduli space of semi-stable. But in general, you get moduli spaces, so you get non-trivial algebraic varieties. So there is no sense in which you might try to count how many stable representations are there. Maybe typically there is just a moduli space of them, and so the answer is just infinity. But there is something special happening if your category is Calabi-Yau, so we already discussed what it means, but if it's actually Calabi-Yau of dimension 3. So what is special about having a category which is Calabi-Yau of dimension 3? The claim is that it's exactly the setup in which you expect to be able to count stable objects. It's exactly the setup in which you naively expect to have finitely many stable objects of a given class. And then if there are finitely many, you might try to count them and get a number. So why is it the case that in this situation you expect to have finitely many objects? So what it means concretely, you expect your moduli spaces to be of dimension 0. And so why is it the case? So it follows from some kind of deformation theoretic type argument. So for example, if you think about the case of sheaves or the case of Fourier representations, this statement might not be so unfamiliar. The fact that tangent space to your moduli space at an object E will be given by the first X group, X1 EE. So this tangent space is a space of first order infinitesimal deformations of your object E. It will be like your tangent space at the moduli space. But in general, if you have first order infinitesimal deformation, you might not be able to extend it to a second order or higher order or true deformations. There are obstructions to do that, which are given by deformation theory. And these obstructions live in the obstruction space at E, which is given by the next X group, which is X2 EE. And what is special about the Calabi-Yau 3 situation is that if you apply the Calabi-Osri version of their duality, you get that X2EE is dual to X1EE. So what is special is that the obstruction space is dual to the Turner space, in particular, has the same dimension. So in general, you might expect your space, so if these obstructions were non-trivial, and if they were really spanning the full of X2EE, you might expect the true dimension of your moduli space to be the dimension of X1, which are like the first order infinitesimal deformation, minus the dimension of X2, because they give you obstructions. And if the obstruction generate everything, you would get dimension of X2EE amount of obstructions. And so if the dimension of the space of obstruction agrees with the dimension of the tunnel space, the kind of expected dimension for your moduli space is 0. It's a difference between these two dimensions. And there is a way to turn this remark into something concrete. So let me first look at the situation where m gamma sigma stable is equal to m gamma sigma semi-stable. So this thing will be a first simplifying assumption we'll need to drop later, which is to assume that for the class gamma, all semi-stable are stable. We assume there is no strict semi-stable, so that the moduli space of stable is just proper. Then it follows from the fact of this duality between x1 and x2, then you can construct on this moduli space a so-called symmetric perfect obstruction theory. And then by the theory of Litian and Baron-Fontecchi, there will be a corresponding virtual fundamental class on your moduli space, which will be a homology class of dimension 0, living in degree 0. And if your moduli space is proper, you can just take the degree of the 0-dimensional fundamental class to get a number, and you get an integer that's denoted by omega gamma sigma. So this omega gamma sigma will be our Donaldson-Thomas invariant. So here, this thing is a definition when there is no strictly semi-stable. When there is no strictly semi-stable, the key point is that if there is no strictly semi-stable, this x0 of EE is under control. It's just C. And by their duality, it is x3. So x3 is also under control. So both S0 and x3 are understood. And then you can build a symmetric obstruction theory from x1 and x2. You get this virtual class, and you get this number. And actually, what I wrote there is essentially the original definition due to Donaldson-Thomas and Thomas at the end of the 90s, where they wrote a version of this definition in the context of Gieseker stable sheaves on Calabi-Osri. So they were looking at moduli space of Gieseker stable sheaves. And under the assumption that there is no strictly semi-stable objects, they cooked up this virtual fundamental class, and by taking its degree, got a number.
May I ask you?
Yes?
The fact that MST is proper follows from the fact that your category is proper.
Yeah, that's right. Yeah. It's related to that, yeah. Yeah, so if it's not proper, then you might need to think about what to do. Yeah. So here, I just wanted to give a picture or an idea of what this number is about, because you have hidden in these words virtual fundamental class some amount of technology. So maybe the kind of simplest remark is that if your moduli space is honestly 0-dimensional, so if x2EE is 0 and x1EE is 0, so your moduli space is honestly smooth of dimension 0, then this DT invariant would just be the number of points in your moduli space. And here I've described a situation which is not the general situation, but which is a kind of toy model situation for what's happening. So in general, it could be that x2EE is non-zero. And then by third duality, x1 EE is also non-zero. So your moduli space might be of positive dimension. And here I'm looking at the situation where the obstruction sheaf, so the sheaf formed by this group x2EE, if you assume it's actually a bundle, so its dimension does not jump, then in this case, the dimension of the x1 also does not jump. So the tangent sheaf is really a tangent bundle, and your moduli space is actually smooth. So here I'm looking at this situation where m gamma sigma is smooth, and the obstruction bundle is a cotangent bundle over it, because x2 is dual to x1, which is a tangent bundle. So in this case, you don't have a zero-dimensional moduli space, but you have a smooth moduli space, and over it you have this cotangent bundle, which is an obstruction bundle. And in this case, the kind of virtual class technology reduces to the following recipe to take the order class or top chain class of this obstruction bundle over the moduli space. And because you take the order class of the cotangent bundle, up to a sign, it is the order class of the tangent bundle, and the integral of the order class of the tangent bundle is just the topological order characteristic of your space. So in this kind of toy model situation, your number is up to a sign given by the topological order characteristic of your smooth moduli space. And so you should think of this order characteristic as being some like virtual replacement for the count of objects. So if the moduli space were zero-dimensional, this thing would just be the number of points. And if it has higher dimension, you just count it via the Euler characteristic. And here, something to note is that there is some annoying sign coming up, which will reappear in many, many other places. And where this sign comes from is the fact that the obstruction bundle is a cotangent bundle, and then the Euler class of a cotangent bundle is related to the Euler class of tangent bundle by a sign. So in general, it's some kind of signed Euler characteristic. So this thing is what happened under the assumption that the moduli space is smooth. And in general, again, as long as there is no strictly semi-stable, this virtual class technology gives you a definition of some number. And here I just wrote some examples of numbers which are special case of these numbers that some people cared about, still care about for different reasons. If X is a geometric Calabi-Yau threefold, you might look at very special sheaves which are ideal sheaves of curves inside X. So you look at sheaves of the form ideal sheaves of Z, where Z inside X is a one-dimensional subscheme. And then, again, if you restrict to this kind of Gieseker stable word, then you can check that there is no strictly semi-stable in this setup, and it's related to the fact that the rank of the ideal sheaves is 1. So there will be, in particular, this vector 1, 0, minus beta, minus n, which is a vector of chain characters. It's a primitive vector. It's not a multiple of any other vector because of this 1. And essentially, for this reason, there is no strictly semi-stable objects. Everything is stable. And actually, in this case, the moduli space is just happens to agree with the Hilbert schemes of one-dimensional subschemes inside X. And then this is a theory of a virtual produce for you a zero-dimensional virtual class on these Hilbert schemes, and then you get some integers. And these integers, so sometimes when people talk about Donaldson-Thomas invariants, in some setups, they only what they really mean is only this particular class of numbers, counting ideal sheaves on a Calabi-Yau threefold. And these numbers are a version of curve counting because they're counting ideal sheaves of curves. So you might wonder if they're related to other kind of curve counting. And one of the main reasons people care about these numbers is that there is this MNOP conjecture, which in this Calabi-Yau 3 setup has been proved recently by John Pardon, saying that these numbers contain the same information as the Gromov Witten invariants of the Calabi-Yau threefold X, which is a different way to count curve. But for the purpose of these lectures, we'll not focus specifically on this count of ideal sheaf of curves. We'll not really do curve counting in this sense. we will really want to consider like essentially arbitrary sheaves. And in a kind of essential way, we want to consider the case where there exist strictly semi-stable objects, not just stable objects. And the basic question is how to count semi-stable objects. And the basic issue is that to get a count having a reasonable property, you might think that every object should count with its automorphisms. But semi-stable objects can have very big groups of automorphisms. For example, if Q is a quiver with a single vertex, then an n-dimensional representation of that is just a vector space Cn. And then there is an automorphism group of this representation, which is just a group of all n by n invertible matrices acting on Cn. So the stack of representation in this case is just a point, spec C, divided by GLNC. Just a point is like a very bad Artin stack, a point divided by this big group. And if you think about the counting we have been doing previously as some kind of Euler characteristic, in this example, you might get that the correct thing to count is to take the Euler characteristic of this stack, which should be 1 divided by the Euler characteristic of GLN. But the Euler characteristic of GLNC happens to be 0. For example, for n equal 1, you have C star, and C star retract on the circle S1, which are Euler characteristic 0. And so you will get something like 1 over 0. And so you get some nonsensical answer, something like infinity. And when there are only stable objects, you might wonder, oh, there is always a C star, but the fact that the C star automorphism is the same everywhere make it easy to get rid of. And in the prehistory, you can think of a prehistory as a way to get rid of this C star. But now when they are semi-stable, this group GLNC, they can move from one point to the other. And so to get rid of them is more tricky. Yes?
So why would we want to divide the characteristic of GLN? Because it's sort of the fiber of this space, this space is moduli split, and the fiber is GLNC. So these are to the minus of this characteristic. So the characteristic is additive, not multiplicative. So why do we consider this quotient? Sorry, this fraction quotient?
Yeah, are you saying we should just look at the kind of the coarse moduli space, maybe? And are you saying this thing does not appear in the coarse?
The question is about why you have a reciprocal instead of like a negative for the Euler characteristic. Like why does the Euler characteristic of H and 1 over Euler characteristic of G?
Yeah, that's one way to say it is that, yes, really it's a fibration. And if you have like a product, the Euler characteristic of a product is a product of Euler characteristics. So you have a point, which has Euler characteristic 1. Yeah. So it's just some multiplicative properties of Euler. Like definitely, like if you have a finite group, for example, then the natural orbifold Euler characteristic of your stack will be the Euler characteristic divided by this order of this finite group. Okay, so the Euler characteristic version of this count does not make sense. But you might say, oh, maybe you should be more refined than the Euler characteristic. Maybe if you replace the Euler characteristic by motivic or cohomological counts, then this thing might make sense. So for example, motivically, you can look at something like a weight polynomial on your cohomology, which for things like GLN reduces. One way to think about it in very concrete terms, you might think about counting points of a FQ. Go from complex number to finite field FQ, and then count points of a finite field. And now 1 over the cardinality of GLN with FQ coefficients makes sense, and it's given by this fraction. And trying to recover the Euler characteristic in this setup, it's related to trying to take the limit Q equal to 1 in this expression. So motivically, this thing is like a polynomial in Lefschetz motives. And you recover the other characteristic of the complex locus by setting q equal to 1. And here you see the poles. You have some pole structure which prevent you from naively taking the limit q goes to 1. And so here is a key identity, which is some elementary looking identity, which was probably known in some form to Euler, which is that on the left-hand side, I wrote this generating series. I wrote a generating series with coefficients as this kind of finite field way to count 1 over GLN, or maybe motivic way to count 1 over GLN. And I sum over n and introduce some extra variable x to the n. And there is something remarkable happening, which is if you take the logarithm, you get something very simple. So the left-hand side is exponential of the right-hand side. And the right-hand side has a very simple pole structure. It's just 1 over, like roughly 1 over 1 minus q to the n. There is not a product of the 1 factor. There's only a single factor. And this left-hand side is something called the quantum logarithm function, because if you write q equal e to the h bar, and if you take some h bar going to 0 expansion, this 1 over n times 1 over this rational function at the leading order in h bar become 1 over n squared. And this sum over n xn over n squared is something called the logarithm function. So there is this identity, and you should think of this identity as being a way to extract something on the left-hand side which has to do with a stack or semi-stable, to extract out of it something which has a much simpler pole structure, and from which you should be able to take the limit q goes to 1 in an easier way. So now there is two things I need to explain. So this thing was just on this example of this quiver with a single vertex. What I want to discuss now is what to do with the stacks of semi-stables. So what will be the analog of the left-hand side in general. And then motivated by this formula, how to rewrite it in a way which looks like the right-hand side and which will be used to define our invariance. So here I will skip quite an amount of details. So the main thing which is used in the general theory is the fact that not only is the moduli space of expected dimension 0, so we have this dimension of obstruction equal to the dimension of the tunnel space, but actually something stronger is true. So it's supposed to look like your moduli stack of objects is supposed to look like the critical locus of a function defined on a smooth stack. So maybe your space is not smooth, but there is a smooth stack, and the function on this smooth stack whose critical locus is your moduli space. And here is a way to believe it should be true at some formal level. If at some formal level you do some deformation theory, maybe I will skip the details. Maybe at the simplest level, if you do some deformation theory in the proper context, you have some maybe differential graded algebra, and you write down something like a Maurer-Cartan equation, something like dA plus A squared equal to 0, which gives you some kind of formal picture of your moduli space. And what is remarkable about the Calabi-Yau situation is that you can rewrite this Maurer-Cartan equation as being the vanishing of the derivative of a function. And locally, your function is something like 1 over 2 a dA plus 1 over 3 a cubed, and then you take some kind of trace given by the Calabi-Yau condition. So actually, this story was a historical origin of Donaldson-Thomas invariance. So the Maurer-Cartan equation looks like a curvature 0 equation. And in the 80s, people were looking at moduli spaces of flat connection on real 3 manifold. And what is special about Schur-3 manifold is that this curvature 0 equation can be written as being the vanishing of the differential, so the critical locus of the so-called Chern-Simons functional, which is this functional 1/2 ADA plus 1/3 A cubed. And the starting point of Donaldson and Thomas was to try to do something not in real dimension 3, but in complex dimension 3. And the observation is that in Calabi of complex dimension 3, you have this kind of formal structure, where the equations defining a moduli space are some kind of zero curvature condition. But actually, this zero curvature condition can be written as critical locus for a functional, which is a Chern-Simons-like functional. So this thing is a formal picture doing some formal deformation theory, but there is something much stronger which is true. Using some derived algebraic geometric language, there's a -1 shifted symplectic structure on the stack of objects. And then there's a version of a Darboux theorem. So the classical Darboux theorem will tell you that a symplectic form locally looks like a standard symplectic form. And here there is a statement saying that this -1 shifted symplectic structure looks like a standard -1 shifted symplectic structure, which is a critical locus of a function. So in concrete terms, what these results are telling us is that in the general context of moduli spaces of objects in Calabi of 3 categories, a moduli space is always locally, can be realized as the critical locus of a function defined on a smooth space. Okay, so you have this picture where your stack of semi-stable is a critical locus of a function f on some stack m tilde, which is a smooth stack. And then each time you have a function, and if you look at this critical locus, on the critical locus there is a natural sheaf of vanishing cycles which remember some kind of information for how the function behaves transversally to the critical locus. So on this critical locus, there is always some kind of sheaf. And then the stack invariance you want to look at is some kind of Euler characteristic of your stack valued in this sheaf. And again, to make sense of that in a stacky sense, maybe you want to consider some kind of weight polynomial or weight rational function. So because of the stacky issue, the left-hand side will be, as before, some kind of rational function in Q with a lot of poles when Q equals 1. So you cannot take the limit Q goes to 1. But you might rewrite this expression in this formal way on the right-hand side, which look exactly the kind of quantum logarithm function I wrote previously, where I introduce some omega gamma sigma of Q to the n, which a priori, if you just do a change of variable to go from the left-hand side to the right-hand side, you might view that as being the definition of this omega gamma sigma of Q. And because everything involves rational function in Q, you get an expression which is a priori rational function in Q with rational coefficients. Because there are also rational numbers in this formula. This is 1 over n.
Is the curve sheet independent of the choices?
Yeah, so this thing is, yeah, so here this thing is kept on purpose. There is also this issue in which sense is this thing canonical or in what sense is it unique. So, and it's particularly important given the fact that this picture I claim is only local. And so if you try to do a global picture, if you want to try to glue these local pictures, this uniqueness or canonicality issue is really important. So the claim is that if you care about the global story, if you have a choice of so-called orientation data, which is some kind of global choice, then at the end of the day, you get something which is unique and well-defined, the sheaf on the modular stack of semi-stable. So at the end of the day, there is a well-defined, maybe some people call it DT sheaf or BPS sheaf, which is kind of independent of choices.
In the case
Yes.
of the quiver with one vertex, no errors, phi is the constant sheaf, and then you recover the.
Yes, exactly. So here is a comment that actually, if you only care about quivers, actually this local story is always realized because you can always take the stack of just ordinary representations of your quiver. And again, this thing will be a smooth stack because there is no x2. And then the moduli space you care about is a critical, like what you care about are the modules of the Jacobi algebra. So representation of a quiver with relation imposed by the potential. And the point is this relation imposed by the potential is a point of having a potential. It's partial derivative of the potential. So it's a critical locus of a function on a moduli space of quiver representations, which is a trace function, which is obtained by taking a quiver representation, and for each oriented cycle, you compose the corresponding linear maps, and you take the trace, and you get this map. So in the quiver context, your moduli stack can be globally realized as a critical locus of this trace function on this smooth stack. And then what you do is, OK, here, I will talk about that in 1 minute. In the previous story, you just take vanishing cycles of that. And so in particular, when W equals 0, you just take like ordinary cohomology, just Q constant shift coefficient.
And this is in N, the Donaldson Thomas are in N, the NQ 1/2, when the quiver is like in the 2D case.
Yeah, like if you have this kind of properness type restriction. If you restrict to this kind of properness type moduli spaces, then you will get this kind of, but actually in N, yeah, is a quite, okay, yes, so in complete generality, there will be no positivity. Yeah, there will be positivity only in special situations. Yeah. So if I come back to this formula, on the left-hand side, there is something complicated having to do with the stacks of semi-stable. And the fact that on this stack, there is somehow this canonical sheaf, which encodes some of the virtual structure. And then we rewrite this left-hand side as the right-hand side. And après, you get the definition of a complicated rational function. But then you have this integrality conjecture, which is somehow motivated. For example, one way to think about it is to think about this example. In this example, the omega would just be essentially 1. And that's it. So motivated by this example, you might believe that more generally, this omega should be a Laurent polynomial with integer coefficients. So there is no poles. Yes?
Go back one slide. So there must be some statement that you can always write it in this way with this x. Is there something that I'm forgetting about?
Yeah, so
So the chi q take value is where?
So yeah, let's say it's a rational function in Q.
So then why can you write it as an x flow? Why is logarithm of this form?
Yeah, so I claim actually there is nothing mysterious. You can always invert this formula. If you are ready to take omega to be a random rational function, there is nothing you can just invert. It's just a rewriting. But the deep conjecture, which is not obvious, is this omega is a polynomial. So if you want omega to be a polynomial, there is no reason for that to be true. And it is where the conjecture is. And that indeed there is something deep about the left-hand side, which is hidden. Yeah, so here, if you do this kind of motivic count, you should think about it as this kind of Q as being some kind of weight polynomial. So you take the cohomology, and there is some weight filtration, and the Q, remember the weight grading. And the point is that this polynomial, this kind of Q, is well defined for any of these stacks, like point divided by a group, because I can always divide by a polynomial. Whereas if I were using the ordinary Euler characteristic, I could not always divide, because sometimes the Euler characteristic is 0, and then I would get some 1 over 0. So this Q is some kind of regulator to have well-defined thing, and at the end of the day, you want to take the limit Q equal to 1. But on the left-hand side, I cannot take the limit Q equal to 1 because there is a lot of poles. But this formula tells you actually all the poles are contained in this simple pole, and then if I look at the numerator, there will be no pole, just be honest polynomial. And then here, I can take the limit Q equal to 1 if you believe this conjecture, and then you get some integer. Yeah. So it's kind of the point of maybe like Deligne type of series. This weight thing is defined for anything. Like there is no smoothness or properness assumption. There is always this weight filtration which is well defined and which has nice like motivic-like properties. So. Oh, is there a typo? Oh, yeah, probably there is a typo. Probably here it should, if there is no things, it should really be semi-stable. Yes, this thing is a typo. Thank you. Okay, so there is this conjecture, and this conjecture has been proved in the setup of query with potential by Meinhardt-Heinecker if W is 0 and by Davidson-Meinhardt for general query with potential. And there is an explanation for this conjecture, which is that this omega gamma of q actually has an alternative direct definition, making it clear that it is a polynomial with integer coefficients. And I will skip the details of this definition. I will come back to it later on. Let me just say that this construction I'm skipping now is sometimes referred to as the BPS Lie algebra. It's something which is very much relevant for quotient representation theory. So it's not something I will talk about much about. In this talk, I will focus on the numbers, on the numerical invariance, but there is some kind of higher structure behind these numbers which are relevant for representation theory. And sorry?
The theorem is the first equality. That omega q.
Yeah, that's right. The fact is omega q has this alternative description. And last time, at the beginning of next time, I will come back about what is this equality. And let me just stop there for today. And if there are more questions, I'm happy to answer. Yeah, so actually there is, in this Darboux theorem, if I'm not misquoting, I think there is a very strong statement. It's like there's a Zariski locally statement. So there is, but maybe if you start talking about stacks, it will be more difficult. So okay, I think for stacks, maybe it's safer to say like smooth locally than it is a critical local. So really the kind of local model, you have a smooth scheme, a function on the smooth scheme, the critical locus, and then maybe you take the quotient stack by a group acting on that while preserving the function. And the claim is that your stack locally looks like that probably for the smooth topology. Like locally around any point, there's a kind of chart. Yeah, that's like smooth. Okay, I guess there is. So that is true. So I think if you could forget the stacky issue, probably you could take Zariski locally. But maybe for stacks that is smooth locally, it looks like that. So in particular, it's much stronger than some formal statement. And it's why there is probably the formal statement will be kind of automatic from this deformation theory here I kind of sketched. But the non-trivial statement is of all these people are related to having something better than formal, but like less formal locally. Yeah.
2 slides after.
Sorry?
Like 2 slides after.
Oh, yeah, sorry. Yeah.
How do you get like the semi-stable part?
Yeah, that's right. Yeah, I understand. Yeah, that's what the thing is a description of. Okay, let me. Yeah, so there is a question, can I just put semi-stable here, and is it still okay, or do I need to be careful? So I think in general, these sheaves, I think they come by restriction for what happened on the full stack without imposing the semi-stability condition. So here it's a description of what happened on the full stack. And then once you have this sheaf, you can just restrict it to the semi-stable locus. I think it's what's happening.